morning. Today we're going to talk about the ratio test specifically, but before we talk about the ratio test for series, we do need a couple of additional definitions. We just finished talking about the alternating series test, which of course was for series with positive and negative terms that alternate. So for a series that isn't all positive terms, that has some positive and negative, we can classify its convergence in two different ways. By the way, we need to talk about this. It's not super important in the sense for me right now, just so that you know the definitions, but I'm not going to be asking you a lot of questions about the different kinds of convergence. But we do need to know the definitions so that when we see them, we know what it's talking about. Okay? So this idea is the idea of absolute convergence. A series is called absolute convergent if it converges in absolute value. Well, that kind of makes sense, right? Meaning, if I have something like this, say n cubed, right? Well, I happen to know, I can of course use the alternating series test to show that this converges, but I know something even more, because the absolute value of the terms is just going to be 1 over n cubed. And that series is a p series with p greater than 1, so I know this converges. Right? So if I'm asked about this series, I can not only say it converges by the alternating series test, which I could say, but I can also say it converges in absolute value. Its absolute value converges, or it's absolutely convergent. Let me contrast that with a different series. Since we're doing p-series, we know if I change this, right, what ends up happening, my absolute value is now 1 over n. I didn't write convergence before, sorry guys. But I know that this one diverges. Okay? So this one diverges, but when I have the n equals, when I have the -1 in there, this converges by the alternating series test. So that was an important example from last week. Okay? So this converges, but its absolute value doesn't converge. So this series does not converge absolutely. We call that converges conditional. So write that up. If the series AN converges, but its absolute value diverges, we say AN converges conditionally. Okay. So these are two examples where you can see that. So what does this mean from the point of view of what am I going to actually ask you about this? Some of the homework problems, I think the homework problem in this section will ask you, does it converge absolutely, does it converge conditionally, or does it diverge? So they're basically like that. And what you'll find out, we'll talk about the ratio test. The ratio test tells you something about the absolute convergence stuff. That's why we need to know what it means. Is it a huge deal? It's just a question of vocabulary, right? So it's still convergent if it's conditionally convergent. I don't really like the way that's named, to be honest, because it's not even really conditional on anything. It's just this converges, but it doesn't converge in its absolute value. Okay? One thing that can be useful here, that you can use this absolute convergence for, is you can use it with series that do have positive and negative terms, but don't necessarily alternate. And we haven't looked at any of those really yet because, you know, we can't use the alternating series test with it if it doesn't go plus minus, right? If it's all kind of messed up, then we can't use it. But so, what am I actually talking about? You can prove very easily, and it's proved in the book, that if the absolute value converges, then the series itself converges. Okay? And so here we're thinking of AN being a series that has both positive and negative terms. And here, if we look at the absolute value, and we can show that the absolute value converges, then we're good with this one. Okay? And so it makes sense. These are all positive. These have some positive and negatives, so it's going to be less. And you can prove it with direct comparison. Fine. So where am I with that? Let me give you an example of where we'd actually use this. Maybe we have something that looks like this. Okay, I'll share. All right. So this is kind of weird, right? Because it's not pi or 2 pi or something, it's n. So if I write this out, I get this. Also 4 minus 1 cosine of 6. No, wait, oh yeah, n squared, good. Like, wait. Plus whatever. Okay? But if I work out these numbers, cosine 2, cosine 4, cosine 8, some of them are positive, some of them are negative, and you don't really know. It's not going to alternate. So we can't use the alternating series test for this because it's maybe be positive, 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 negative, 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 whatever. Whatever it is, it's not alternating. So for something like this, you can use this idea. If I do the absolute value of this guy, this is this, right? But cosine of whatever it is going to be less than 1, right? So by direct comparison, if we know this converges, my absolute value converges. Or this guy converges absolutely, which means it converges, right? So my conclusion would be, I can actually write it this way. My conclusion would be that this guy converges in absolute value, so I can say converges absolutely. Okay. One other thing I want to point out, if you have a series that's all positive terms, you take the absolute value, it's still the same series. So it's going to converge absolutely if it converges, by default. So really this classification of converging absolutely versus converging conditionally is strictly for series that have both positive and negative.